we now have a new function, the function e to the x. It makes sense to ask if we can differentiate this function. So we're going to try to do that, and we're going to use the laws of exponents to accomplish that. So remember, the derivative, since we have to start back at our limit definition, we have the limit as delta x goes to 0. We always have to have that in front. We have the function at x plus delta x minus the function at x, all divided by delta x. Of course, the first thing that we want to do is put in the function itself. So f of x is e to the x. So this first part is e to the x plus delta x. Then we just have e to the x, and it's all over delta x. Now where do we go from here? Because somehow we want to cancel out the delta x on the bottom. Well, the first thing you can notice is that we have e to a sum of two numbers. Remember, we have a law of exponents. Let's kind of put this in a box off to the side over here. The e to the x plus y is the same thing as e to the x times e to the y. That's our first law of exponents. The way we wrote it before is that we went the other direction, but there's no reason why we can't go both ways. So here, we're going to turn this into an e to the x times an e to the delta x. And then one thing you might notice now is that every term on the top has a factor of e to the x. We can actually factor that out. And in fact, because e to the x doesn't have any delta x's in it, we can pull it completely out of the limit. Just pull e to the x out entirely. Note that all the x's are out of the limit now. We have an e to the x on the outside, but the limit here only involves delta x's. That means that this limit is just some number, and we want to know what the value of that number actually is. Now we could go ahead and test some small values of delta x and try to see how it goes from there. But we're going to actually go back to the definition of e to get an idea. Remember our definition of e that we used? So that e is the limit. Well, before we had as x goes to 0 of 1 plus x to the 1 over x. Instead of putting x in here, I'm going to put a delta x, just to kind of match what we had in our derivative formula. The actual variable shouldn't matter in this definition. Okay, so how does this help us? Well, remember that this is the limit as delta x goes to 0. That means if delta x is close to 0, so as long as delta x is close to 0, that means e is going to be approximately, it's not going to equal, but it's going to be approximately this function. Let's take the delta x power both sides. I'll get rid of the 1 over delta x that we have over here. So we have the e to the delta x is approximately equal to 1 plus delta x. That's a pretty decent approximation for e to the x, only it does require that we be very close to 0 to do so. But that's actually all we need for our limit up here, because we are taking the limit as delta x goes to 0. So I can essentially substitute in that approximation in for this e to the delta x. Basically, the limit as delta x goes to 0 of e to the delta x minus 1 over delta x. That's the limit from the previous page. This is going to be equal to the limit as delta x goes to 0 of, instead of e to the delta x, I'm going to put 1 plus delta x. And I still have the rest of the stuff. We have a minus 1, we have over delta x. And where do we go from here? Well, here we can actually go ahead and cancel stuff. We have the 1's cancel out. Now we have the delta x's. Delta x divided by delta x is, of course, just 1. So we could write this as the limit of 1, but, well, the limit of a constant is just that constant. So we literally just get 1 for this limit. In other words, we have e to the x times a number which just turned out to be 1. So we have 1 times e to the x. In other words, we can go ahead and actually write this down as a formula. The derivative of e to the x is just e to the x. E to the x is a function whose derivative is actually equal to itself. That was something we did not have before. Whenever we dealt with polynomials, we ended up with a polynomial that had degree 1 less than we started with. Say x squared became 2x. It was a smaller degree. There's no way we can get a quadratic from a quadratic when we differentiate. That actually is true for any power. But e to the x is different. E to the x actually has a derivative that's equal to itself. We can also go ahead and write this in a chain rule form. So if we take the derivative with respect to x of e to some function, we're just going to put u here. Remember, we take the derivative of the outside function, which is the e to the x part. So we have e to the whatever power, the same power that we had before, because we're following this formula. But then we need to multiply by the derivative of the inside. The derivative of the inside, derivative of u, is literally just derivative of u. This is what you would find in the table of derivatives in the back of the book, or pretty much any other table of derivatives that you might find out somewhere else. But it's really just coming from the fact that we know that the derivative of e to the x is itself. Note that this works specifically because we use e. If we wanted to differentiate, say, g of x equals a to the x, there's some other generic exponential function, we would be able to follow a lot of the same rules, a lot of the same starting points, where we are able to essentially pull a to the x out of our limit. And we end up with the limit as delta x goes to 0 of a to the delta x minus 1 over delta x. This particular limit here is some number that depends on what a that we're using. Whatever our base is, we're going to have a different limit here. It turns out for e specifically, this limit is 1. But for other numbers, it's not going to be 1. In fact, e is the only base where that actually does come out to be 1. Now, it's not really clear what this limit should actually be. We will find a way to answer that question in a later section. We're not at a point where we know how to do that yet. In fact, we're probably going to approach that question from a slightly different perspective. But it is kind of interesting that even though we can't finish the problem, we can tell that if we start with an exponential function, regardless of the base, then the result is that same exponential function times some number. So they kind of have the same characteristic as e to the x, it's just not quite as nice. Now that's really all we had to talk about in this section. We have one function that we wanted to find the derivative of. We have the derivative of e to the x now. We're all good. But let's go ahead and put that together with the stuff that we already knew and actually differentiate some functions. See how it behaves in the wider scheme of functions. We're going to start with problem 3. Here we have y equals e to the 5x, and we want to differentiate this function. Now remember, we do need to use the chain rule here because we don't have just x in the exponent. We have to treat 5x as the inside function. So y prime, we differentiate the outside function of e to the x. We just get e to the x, or 5x in this case. And then we multiply by the derivative of the inside. Derivative of 5x is just a 5, which we would probably write that as 5 times e to the 5x. Go ahead and put the number out in front. But you kind of see this kind of form pretty often. Remember, when we had our compound interest stuff, we had a equals p e to the rt. If we were to try to differentiate this thing, we use the same idea. Well, the p out in front is just constant, so it just stays there. But we have to use the chain rule for the rt up in here. And that basically, you can notice that what we did with the 5, we basically just got to multiply by 5 on the outside. This r, we multiply on the outside. But it doesn't change the e to the rt, because the e stuff actually just turns into itself. So it's useful to kind of remember how it works for just a constant in the exponent, because it comes up in a lot of applications. What if we have something slightly more complicated, though? In problem 7, we have a 7 times e to the minus 1 over x squared. So this minus 1 over x squared is all in the exponent. This is one situation where you might use the alternate notation. This way it makes it very clear that all this stuff is inside the exponent. But a lot of times people will just go ahead and write it this way anyways. Alright, so we want to differentiate this thing. Like I said before, the 7 is just a constant. It just sticks around. We have e to some power. We differentiate that. We just still have e to that same power. But now we need to also multiply by the derivative of the inside. We need to multiply the derivative of that stuff in there. What is the derivative of negative 1 over x squared? Well, remember, 1 over x squared is x to the negative 2 power. So we'll take the negative x to the negative 1 over, x to the negative 2 power. We bring down that negative 2. It's going to combine with the negative that we already have and just give us a positive 2. And then we're going to lower the power of negative 2 to a negative 3. We can actually go ahead and turn this back into a fraction. In fact, I'm going to go ahead and combine the 7 and the 2. So that becomes a 14. We're going to have an x cubed on the bottom. And we still have the e to the minus 1 over x squared. Okay. Let's do problem 9 next. Y equals 4x cubed e to the minus x. So note here that we do have e to something other than just x. It's just a multiple times x, so it's pretty easy. But we also have a product. And our product rule still works. The product rule did not assume that we were just dealing with powers. It also works for exponentials as well, just like the chain rule did. So when we differentiate this thing, we need to use the product rule. That means we take our first piece with 4x cubed, and we differentiate it. Of course, that means we bring down the 3 to make the 4 12, and then we reduce the 3 to a 2, and we leave the e to the minus x alone for the moment. In the next term, we add, now we're leaving the 4x cubed alone, but we're going to differentiate e to the minus x. But since it's e to some constant times x, this constant being a -1 here, we basically just get to take e to the minus x and multiply it by that number. We multiply this by -x, or by -1, which is just going to change our plus sign into a minus sign. And note, whenever dealing with some polynomial times e to some power of x, or e to some constant times x, we always end up with these e to the minus x's in each of our terms. We can actually go ahead and factor that out. It looks a little nicer that way. In fact, if we want to continue factoring stuff, we could pull out a 4 and an x squared as well. This is left with a 3. This one's left with an x. Of course, that's not completely necessary to be written to have our derivative, but it's kind of a nicer form. In fact, in a lot of applications, this might be easier to work with. For instance, if we were trying to find critical points, it's a lot harder to find critical points here than it would have been here. Let's look at problem 13. Here we have another function. F of x is equal to e to the x plus 1 divided by e to the x minus 1. This is actually a well-known function, well, at least sort of. We'll not get into that here, but we can go ahead and still find its derivative. Now, of course, we do have to use the quotient rule here, and the quotient rule works exactly the same way when involving exponential functions as it does when we're just doing polynomials. So the derivative here, remember the quotient rule, we take the derivative of the top, derivative of e to the x plus 1. Well, of course, we know that e to the x becomes e to the x. The plus 1 actually just goes away. So we have an e to the x. Now we need to multiply that by the bottom without differentiating this time, minus the top, as it already is, times the derivative of the bottom. The derivative of the bottom, of course, the e to the x stays the same. The minus 1 goes away. And then we have the bottom squared. Let's go ahead and actually simplify this a little bit. We can distribute the e to the x to each of our terms. E to the x times e to the x. Remember, when we have the product of two exponentials like that, we add their exponents together. We get x plus x. We get an e to the 2x power. E times -1, of course, is just a negative e to the x. Here we do the same kind of thing. Remember to distribute that negative as well as the e to the x. So we have a minus e to the 2x. And then we have a minus e to the x. And look at that. We have an e to the 2x here and a negative e to the 2x here. The minus e to the x's actually just go ahead and combine into a minus 2 e to the x. And we can't really simplify that with the bottom at all. So that is our derivative of our function. Moving right along, let's look at problem 24. Here they're giving us a function, 3x over e to the x, but they don't want us to just find the derivative. Instead, they want us to find the equation of the tangent line to whatever the graph of this function is at a particular point. When x equals 1. Of course, when x equals 1, we have to plug that in here, and we get a y value of 3 over e. Which that's just a little bit over 1. But how do we find the equation of a tangent line? Well, if we have a point, we need a slope as well. We're going to use the derivative to find the slope. So we need to differentiate this thing. We can go ahead and use the quotient rule. Another way you could do this actually is to turn an e to the x on the bottom into an e to the minus x on the top, and treat this as 3x times e to the minus x. And then we could use the product rule instead. The quotient rule and the product rule are kind of the two sides of the same coin. So whichever one you want to do here is up to you. I'm going to go ahead and just use the quotient rule. So I take the derivative of the top, which is a 3, times the bottom, that's e to the x, minus the top, 3x, times the derivative of the bottom, well, that's still just e to the x. And then the bottom squared, we just end up multiplying the x by 2. But actually, everything has a factor of e to the x in it. We can essentially cancel an e to the x from both these terms on top with one of the e to the x's on the bottom. Remember, this is e to the x times e to the x. So really, we can write this as 3 minus 3x over e to the x. You could even pull out the 3 if you want to. Now, of course, we're mostly interested in what happens when x equals 1. What is y prime of 1? If I plug 1 in here, well, we have 3 minus 3 on top. Well, you probably see right away that that's all we really need to know, but the bottom does become just an e. But this just becomes a 0. That means our tangent line since we have a slope of 0, we have a horizontal line, and so the equation of that line is just going to be y equals whatever the y value of the line is. Well, we already know that y value is 3 over e. We can even go ahead and take a look at it. Let's just graph y equals 3x over e to the x. We get this little graph here. When we look at the point 1, 3 over e, that is the point here. And as you can kind of tell, it is actually at a relative maximum. And that corresponds to the fact that we know the derivative there is equal to 0. So if we just graph that horizontal line that we said, we just get a line that touches our graph right at that point. That's exactly what we expected to see. Let's do another problem like this. Let's look at 25. Here we have another function, y is equal to e to the 2x power plus 1, then cubed. We're still trying to find the tangent line at a point. This time the point is 0, 8. So we do the exact same thing. We take the derivative. Keep in mind here that we have a function inside of a cube, so we're going to use the chain rule once at least. So we'll take that cube out. We take whatever's already inside there to 1 less power, so we have a squared. But now we need to multiply that by the derivative of the inside. Well, when we differentiate, the plus 1 goes away. The e of the 2x, technically we need another chain rule. This time it's just e to a constant times x, so we know how that goes. We just get to pull out that constant. And we can go ahead and simplify this if we wanted to, like combine the 3 and the 2, but that's not really too important here when all we're trying to do is find the derivative at a particular value. So like up here, we plugged in 1 and just got a number. That's all we're looking for, is what that number was. Here we're going to plug in 0. So what do we get if we plug in 0? Well, the 3 is still there. Here, remember, e to the 0 power is a 1. Then we still have the 2 here, and again, e to the 0 power is 1. So we have a 3, we have this is 4 when we square the 2, and a 2. So we get a slope of 24 when we multiply all that together. That means our tangent line. Well, normally we'd have to go ahead and use the point slope form, but since our x value is 0, this is actually the y-intercept anyways, so we might as well just go ahead and use the slope-intercept form. We have y is equal to our slope, 24 times x, plus our y-intercept of 8. If we go ahead and graph this, remember our function was y equals e to the 2x plus 1 cubed. It's kind of steep over there. But at the point 0, 8, it's a point on our graph, it's our y-intercept. We have the supposed tangent line of y equals 24x plus 8. And that just hits right there at that point. Actually, it's hard to distinguish between that and the function, but you can kind of tell that that looks pretty much correct. And it is exactly correct. But we just wanted to make sure from our graph. Now I want to do one last problem. I'm going to do problem 37, but this is going to actually be a relatively longer problem. Because we're going to take a function, f of x is x cubed, or not cubed, x squared e to the minus x. And the instructions here are analyze and sketch the graph of the function, label any relative extrema, points of inflection, and asymptotes. So we're going to take this and we're going to do all the different things that we had back in, I think it was 3.7. We're going to analyze this to the extreme. So where do we start? Well, if we're trying to start here, we might as well start with our domain. What is the domain of this function? Well, e to the x doesn't have any problems with anything put into it. So unlike with, say, fractions and square roots and all that, whenever we involve an e to the x, it does not reduce our domain at all. In fact, there's no number that can't be put into this formula. Our domain is all real numbers. Next, we want to see where is this positive or where is it negative. Maybe we'll go ahead and do that on a separate page. We'll start with setting this thing equal to 0 and solving it. Now, the very first thing, and this is why I wanted to bring up this problem so much, is that e to the x is never equal to 0 for any x. In fact, this can never even be negative. It can't be negative, it can't be 0. We will frequently run into problems where we set something times an e to some power equals 0. The e to the some power can never equal 0. If you have a problem like this, you can immediately take that part out. This can only be 0 when x squared is equal to 0. That's a hard, fast rule. And that saves us a ton of work, because we can immediately solve that to get x equals 0. So we'll go ahead and make a number line. This will be for the original function f. We'll have 0 on here. We'll go ahead and take some test points. What is f of, let's go with minus 1 and 1. Remember, our function here is x squared e to the minus x. So we get to take a negative 1 squared e to the positive 1, and a 1 squared e to the negative 1. Well, the 1 squared is a positive 1. E to the 1 is an e. Here, obviously, we just have a 1 in front. E to the minus 1. You can treat that as 1 over e. But the important thing is that both these are positive numbers. So you get positive and positive. So it may hit here at 0, but it actually does not stay. It never actually crosses the x-axis. It just stays positive until it just dips and hits the x-axis at 0, and then goes back to being positive. Next up is the derivative. What do we do with the derivative? If our function is x squared e to the negative x, then f prime of x We're going to have to use our product rule here. Take the derivative of the first part, which is 2x. We leave the second part alone. Then we add the x squared, as it already was, times the derivative of e to the minus x. Of course, we've already seen that before. We just end up getting to take e to the minus x and multiplying it by a negative. And we're going to take this thing, we're going to set equal to 0. Now, this looks more complicated than it actually is. Because we have an e to the minus x in both of our terms, we can go ahead and factor that out. And now we can use the fact that e to the minus x is never equal to 0. So this is why I did that factorization back in the other problems. Because it turns out that a lot of the times that's exactly what you want to do. If you have e to the x involved in some sort of product, that e to the x will be in both the terms that you get after you take the product rule. And factoring that out can be very helpful whenever you're doing anything with critical points. So this just boils down to 2x minus x squared is equal to 0. We can go ahead and solve this by factoring. I'm just going to pull an x out of it, which means that x has to either be 0 for this part or 2 for that part. Those will be where we have our critical points. Now note, we don't have to worry about where the derivative doesn't exist. The e to the x does not change that. It's all real numbers still. So for a derivative, we have 0 and we have 2. We need to take some test points though. So below 0, we might as well take negative 1. Between 0 and 2, we might as well take 1. And after 2, go ahead and take 3. Remember, our derivative here is this thing here, or we can go ahead and use the factor form if you want to. If we plug negative 1 into 2x minus x squared, we have a negative 2 minus 1. We actually got a negative 3. Then e to the minus 1 is just e to the first power, or e. Specifically, this is a negative number because of the negative 3 in front. If we plug in 1 instead, now we have 2 minus 1. That's actually just a 1. Then we have e to the minus 1. Even though there's a negative in that, it's just a 1 over e. This is a positive number. Finally, if we plug in 3, now we have 6 minus 9. That's a negative 3. E to the negative 3. Of course, e to the negative 3, again, is just a positive number. It's the fact that we have a negative 3 in front that makes this negative. So we have a negative, positive, negative. And now we go ahead and take our second derivative. So starting with our formula for the first derivative, we differentiate it again. We still have to use the product rule here. We have the derivative of the first part, this polynomial here, is a 2 minus 2x. That'll be multiplied by e to the minus x. Now we're going to basically take the same 2x minus x squared, but we'll multiply by the derivative of e to the minus x. Of course, that will give us a negative e to the negative x. And I'm going to go ahead and combine this. So everything here has e to the minus x times it. I get to basically combine these two things. But remember, we do have the minus sign here. So we'll have a 2. We'll have a negative 2x and a minus 2x again, so a minus 4x. And then we have a negative x squared, so a plus x squared. And we're going to be setting this equal to 0 to try to find any inflection points. Once again, once we set it equal to 0, the e to the minus x really isn't involved. Really, we're just trying to set 2 minus 4x plus x squared is equal to 0. Now, you might say, well, why don't we put the x squared in front? So that we can say this is x squared minus 4x plus 2. Now, we cannot factor this one. This one is a little bit more complicated than before. I'm going to go ahead and use the quadratic formula. The answer is not too bad, but we can't find it by factoring. So remember the quadratic formula, we have negative b, but b is negative 4 already, so we have a positive 4, plus or minus the square root of b squared, so negative 4 squared is 16, minus 4 times a, which is a 1, times b, c, which is a 2, all over 2 times a. Of course, a is 1 again. So we get a 2. Now the inside here, 16 minus 8 is 8. So we have 4 plus or minus square root of 8 over 2. But we can go ahead and actually cancel here. We can go ahead and divide 4 by 2 to get 2. And we can divide, when we divide the 8 by 4, because we have to bring that 2 inside the square root, we actually get a square root of 2. So they're not integers, and they're not even fractions, but as far as irrational numbers go, we could have done worse. 2 plus or minus the square root of 2. If we make our number line, we have 2 minus square root of 2 and 2 plus square root of 2. Now we do need to go ahead and use test points to figure out whether or not we do have a positive or negative for our second derivative. Of course, right in between these, we might as well pick 2. These are actually symmetric around 2. To find out test points for the other ones, remember square root of 2 is like 1.4, so 2 minus square root of 2 is going to be between 0 and 1. I'm going to go ahead and pick 0 for this particular interval here. Same thing over here. 2 plus square root of 2 is between 3 and 4. So I'm going to pick 4 over here. But I'm going to go ahead and have to plug those into my second derivative. We have 0, 2, and 4. If I plug 0 into here, then we have 2 minus 0 plus 0. We just have a 2 here. Of course, e to the 0 power is 1. So literally, f double prime of 0 is 2. This is definitely a positive number. If I plug 2 in there, we get 2 minus 8 plus 4. That turns into a negative 2. Then we have e to the minus, e to the negative 2. But the e to the negative 2 is not going to change the sign. It's the negative 2 in front that tells us that we have a negative there. Finally, if we plug in 4, we have 2 minus 16 plus 16. The 16s actually cancel each other out. We get another positive 2. This time times e to the negative 4. But again, it's the number out in front of the e that actually affects the sign. This is a positive number. So we do go positive, negative, positive. Alright, so let's try to get a graph of this thing. Well, first let's go ahead and plot our points. We have 0, 2, and these two numbers here that are important. If we plug in 0, of course, the x squared in front is going to give us 0 overall. We already knew that. We knew it was an x-intercept at 0. So, in fact, our x-intercept and our y-intercept are both the same thing right now. But we also have other points. We have, when we plug in 2, we notice that we are going to get a relative maximum because we did go from increasing to decreasing. But we do need to know what the y value actually is. So we have to go ahead and plug 2 into here. I went ahead and used a calculator for that and found a y value of 0.54, approximately. I also went ahead and put these in. And again, just using a calculator to give me numbers I can go ahead and plot. So I know where they are relative to the integers and all that. 2 minus square root of 2 is actually equal to 0.586 and so on. And when I plug that into my function, which was kind of fun to actually have to do, got 0.19. Same thing if I go ahead and put in 2 plus square root of 2. 2 plus square root of 2 is actually about 3.414. And plugging that into my function, I got a y value of 0.38. So that'll help us a little bit to actually plot stuff. So notice here that we do want to go out to about 4, just because we want to go to the next integer after that one. Notice that we do have only positive numbers, so that's why I drew my axis without too much on the negative side. Everything's going to be above the x-axis. I don't have to go up too high, actually, so the highest of our significant points is actually not even at 1. So I'll go ahead and put 1 fairly high up on here, and we'll go up to 2 there. And we'll go ahead and plot our points. We have 2 comma a little bit more than a half. We have a little bit more than a half here, so about here, and then not very high up at all, is it? It'd be maybe around here. Then we have maybe around here-ish. Those are our points. This would be 2 comma 0.54. This is 3.414 comma 0.38. And this one over here is the other one. And of course we have our origin point. Alright, so I know it's decreasing and concave up at the beginning. It actually is going to be fairly steep here, though it might not be obvious that that's going to be the case. But then it's going to become increasing but still concave up, so it still has that cup shape to it until it gets to that point there. That's our inflection point. At that inflection point, it's going to start being concave down. It's going to have that cap shape, but it's still going to be increasing until it gets to 2, at which point it's going to start decreasing. So we're going to have something that caps off at 2 until it gets to this point over here. In which case, it's going to still be decreasing, but it's going to be concave up. It's going to have that cup shape again. But notice that even though it will never stop decreasing, in fact, this function will decrease as x goes off to infinity, but it never goes negative. It never hits the x-axis ever. So it's going to be constantly decreasing, but approaching some asymptote. And it might be a little hard to see exactly what that asymptote really is. We basically have to think about what would be the limit of this function as we let x go to infinity. The limit as x goes to infinity of x squared e to the negative x. What is this limit? That's not entirely obvious. In fact, it's a little tricky to do without having a particular theorem. But for whatever reason, I don't think our book ever actually even mentions this theorem. You might actually hear about it. It's called L'Hopital's rule. I'm not going to go into what this rule is. Just I guess be aware that it is a rule that helps with taking limits. Specifically limits where we're dealing with one of our indeterminate forms. And it actually does require us to know stuff about derivatives to use it. But using that rule, we can actually show that this turns out to be 0. In fact, the limit as x goes to infinity of x to any power times e to the minus x is 0. Essentially, e to the minus x goes to 0 faster than any power of x can actually compete with. So this could be x to the 2000th power. That's a function that grows really, really fast. But e to the negative x goes to 0 even faster than that, and can't completely overwhelms the growth of that power. So that's a little bit of an aside, but I think it's kind of important, and I wish the book would actually talk about it a little bit more. But the point is that we were able to get a graph. And we didn't really need to necessarily find that limit in order to know that there was an asymptote. It just told us what that asymptote actually was. If we go ahead and graph it using GeoGebra, so we do have our modern technology, we can go ahead and kind of cheat the system a little bit. We can go ahead and graph x squared times e to the negative x, and we get exactly what we expected. It comes down, hits down here at 0, 0, then goes up and caps off at 2, and then eventually approaches 0 as we go off. We can even go ahead and graph our points. We have 0, 0. We have 2, comma, I'm just going to use f of 2, because it will calculate that for me. Then we have 2 minus square root of 2, comma, f of that. Keep hitting the closed parentheses instead of the open one. And that's throwing things off. There we go. So notice that we do get the points that we got. They rounded to only 2 decimal places in the for the 2 square root 2 minus square root 2 and 2 plus square root 2. But we get exactly what we expected. Alright, so I'm going to leave that here. Obviously, this section is all about what is the derivative of e to the x. We know it's now e to the x. And the rest of it was just about, well, now that we know it's e to the x, we can go ahead and put it with all the other functions that we know, and we can use all of our rules that we already knew about derivatives. It just fits right in, and everything works out just fine. In the next section, we're actually going to stop talking about the exponential function, directly anyways, and we're going to start talking about logarithms. But logarithms do come from the exponential function, and so we'll continue having to talk about it for that reason. But I'll see you guys in that next video.